For the foreigners, what I'm going to do is I'm going to address the crowd in Mandarin first, and then I will talk to you guys in English later. All right? 所以大家好，各位早安。我就是 Thomas Lin， 就是办前瞻的负责人。很欢迎大家到第4届，也是最后一届在台北的前瞻会。很谢谢大家的支持。那这一次呢，我很肯定的说，将是最好的一次在台湾的前瞻。我也相信，也是在台湾这个新西会历史以来将是最好的一个会议。我们总共聚集了10个非常好的讲师跟议题，希望大家都会从这次的会议获取到一些知识，或者是对某些技术上的更加了解。然后我们如果大家想知道我们为什么这次将是最后一届前瞻，因为我们连续亏了4年的钱。然后我现在有一个小宝宝了，我不能再亏钱。好，然后就是最后一年，可是今年也会办得最好。然后希望你们大家多多支持。再来一件事呢是我们今天将有一个你们台湾应该叫做联谊会吧，对不对？我们办了一个 party， 是让大家去的 party， 大家都会被邀请去 party， 而且这个 party 就在这的底层，将有吃有喝的，好不好？然后你们就有借这个机会跟所有的讲师都能交流一下，所以我们希望你们大家都会来参加这个 party。我们这个 party 就是希望大家都会来，要不然的话就很多食物跟那个食物都会被浪费掉。不希望大家会，我们这 party 会在6点开始，就是会议结束后马上就到楼下去参加这个 party， 好不好？反正5、6点这个时间交通很塞，你们就不要在路上塞好，就在先吃饱饭交流一下，大家才回去。好，希望大家都会来。然后你们的卡片里面都有一个餐券，有2张餐券，今天午餐跟明天的午餐餐券，跟 party 的那个餐券。好，到时就把餐券交给这门口负责的人就可以了，好不好？再来一件事就是，我们在这里设了一个无线网，无线网的密码是 SyScan'11 SyScan'2011，好不好？所以你们可以通过这个无线网来上网，如果有需要的话。好，我再重复一次 SyScan'2011，好不好？然后还有的是，我们今年也会给所有参会者，你们可以去试用一个叫 Canvas 的软体。我想请问大家有没有听过 Canvas 这个软体 ？Canvas 是一个测试的软体，就是来做安全测试的，是非常非常好的安全测试的一个软体。然后这个如果你们想试用这个软体的话，请到外面的柜台，你们会看到有些公司叫新友科技的 NFI， 找他们拿一张表格，把你们的资料填好后，我们就会发 email 给你们，你们就有办法去下载从美国的这个软体 Canvas， 那你们就可以试用。我相信这个试用期应该是2个星期或者是4个星期，我忘了这个是有多长，反正就是可以试用 Canvas。这个软体，希望你们大家也会去填表格来下载这个软体。OK， 然后最后一件事，我想说的就是，我们虽然不再办会了，可是我们希望能在台湾找几位这个安全的研究员。如果那些有兴趣参加我们的公司、参加我们的行列的话，请你直接来找我。我觉得薪水还不错哦，所以有兴趣的人，直接来找我，我是叫 Thomas， 我这2天我都会在会场，好不好？所以再次的谢谢你们的支持跟到来，然后希望你们这2天都会对这个会议有好的评语，好不好 ？OK， welcome to Taiwan for all the foreigners and for all those of you who doesn't understand Mandarin. This is the 4th SyScan in Taipei, and it is going to be the last SyScan in Taipei. But I assure you, this is going to be absolutely the best SyScan in Taipei. In fact, this is going to be the best security conference in Taiwan ever. What we have done is we've gathered 10 of the top speakers to speak over the next 2 days. Very good topics, I assure you. All right, and I mean, we have people like Tavis, aka Bug Killer. We have Hava, and 8 more very outstanding speakers. You'll get to know them throughout the 2 days. That's my baby crying. Okay. For those of you who wants to have access to the internet, we have set up a Wi-Fi. The password is SyScan'2011. SYSCAN 2011. It's a very safe network, I assure you. All right. Yeah, seriously, do your internet banking, encrypted email, do it. So that's for the password. And today, after the conference, right after the conference, we're going to have a networking party for everyone. So everyone is invited. It will be at the basement, in a hall, and we have food, drinks, open bar. All of you are invited. All of you are welcome to join the networking party. We hope you will take the opportunity to mingle, socialize with everyone. All right. So that's the whole idea of the networking party. Please do show up at the networking party. We have lots of food and lots of drinks and lots of alcohol. Don't waste it. All right. Okay. Let me see what else do I have to say. Oh yeah, and what I said to the Taiwanese audience was that even though we're not organizing SyScan anymore, we hope to continue to have our presence in Taiwan. And what we want to do is to, if possible, recruit security researchers. So if any of you are interested to work in Taiwan as a security researchers, please just come right up to me and talk to me, and we'll work out something. All right? And if you have any questions, please feel free to approach any of my crew, talk to them, and I'm sure, or myself, and we'll be more than glad to help you. Those of you who needs receipts, tax invoices, talk to Isabel, that's the pretty lady out there, and she will sort it out for you. All right? 我忘了一件就是发票的事。如果你们谁需要发票，或者是发票上出了一些问题的话，请找蔡小姐。蔡小姐就是那个宝宝的妈妈，她就会帮你们搞定所有发票的事，好不好？如果没有什么问题的话，我们现在就开始第一个讲师。好，我们现在热烈的掌声欢迎 Tavis Google 的 Tavis Ormandy。Tavis。Tavis will be talking about Sophos Antivirus. All right. Tavis 的议题将是跟那个 Sophos 的扫毒软体有关系的。
So antivirus vendors often claim that they have to be protected digitally, because if bad actors understand their work, then it's going to weaken their product, which is a problem for everybody. But I tend to disagree with this. If those examination of any security system weakens it, then the system must be fraud. Otherwise, you're just relying on security to security analysis, which is obviously wrong. So the way that antivirus so this talk is going to present the results of an investigation into Sophos, and I'm going to analyze some of the product names that the vendor makes. So I'm not a malware researcher, and I'm not interested in malware at all. My research is primarily vulnerability discovery, exploitation and mitigation, and I tend to focus on low-level system security. So antivirus is interesting to me because it's some kind of mitigation system. It's a large exposed attack surface that's almost ubiquitous on Windows networks. So this talk is for the perspective of a vulnerability researcher, and yeah, I don't work with Sophos. This isn't sales pitch. So there's not much intersection between the work of a vulnerability researcher and malware methods, antivirus methods. This is because malware is a post-compromise concept. Malware is only interesting if you can already execute with the permissions of your victim. And typically this would just be access to a user who can't make trust decisions. For example, you just send them an executable and they run it, and that's the attack. This isn't very interesting to vulnerability research. It's true that you can combine malware with it could be the payload for an exploit, but we would tend to respond differently. Antivirus vendors would try to find every single sample of this exploit and then blacklist it, whereas obviously we try to mitigate things that don't work. So most security researchers work on the assumption that users make good trust decisions, and then we try to find ways to support that and get around that, and still execute code or bypass whatever decision you were making. But antivirus vendors work on the assumption that users can't make trust decisions, and then we try to compensate for that, and so that's where our work is. So unfortunately, the sad thing about this is the antivirus vendors are actually right, because many users just cannot make trust decisions, or they're either unwilling or unable to make trust decisions. And maybe that's fair enough. It can be complex and confusing to do it properly, especially for Windows users. On systems that have good package management, for example, it's not so much of an issue, but it's certainly in case it can be hard to do for particular end users. So antivirus vendors and in general vulnerability researchers tend to agree that the solution to this problem is to offload the trust decision to someone who is capable of making that decision. And where we diverge is how to implement that process. So the solution that antivirus vendors propose is basically a blacklisting scheme. So this isn't so people understand how this works, and people understand antivirus is imperfect and it's generally reactionary. But most people believe that it's better than nothing. Of course, it's always going to be imperfect by definition, because there's an infinite set of possible malware, and blacklisting is always reacting to new samples that we discover. But perhaps it's still reasonable, and the only way to evaluate this really is to find out whether the increase in attack surface that you're going to use for running this antivirus is it going to reduce your overall exposure. So it's an unfortunate fact that we simply don't know how to build perfectly secure systems, because all software has a non-zero defect rate. The best we can do at the moment is really to raise the cost of a compromise to evoke the potential value of that compromise. And there's no reason that security products can't be a legitimate part of that. The general classes of legitimate security products are those that reduce the attack surface of a system, for example, a firewall. Obviously, when you add a firewall to a new network, then you're increasing the attack surface because you're adding this new network stack next to it, and pass apples and so on, and filter packets. But the overall effect from adding the firewall should be a reduction in the overall attack surface of the network, because now it's protecting the system behind it. And there's also those systems that increase the attack surface, but in exchange for strengthening or enforcing some weak security boundary. So a typical example would be like a two-factor authentication scheme. So antivirus would fall into this is the second category. So antivirus promises to reduce the need for users to make trust decisions in exchange for a pretty dramatic increase in exposed attack surface. Maybe this makes sense, because if your users are permitted to make trust decisions and they just simply can't do that, then maybe it's a good trade, because you clearly need to use antivirus urgently, because it's such a major problem. But to be able to understand whether this makes sense, whether antivirus is actually doing what it claims to do, we need to be able to evaluate what it does and understand how it's doing that. This simply isn't possible because antivirus vendors just don't publish any documentation about how they work. So some of the questions that people should be asking if they're considering deploying something like this is how much effective is it trading, how effective is the solution going to be, and does the vendor really understand the problem they're trying to solve? So yeah, vendors just will not tell you what it is they do. And it's impossible really to verify how the techniques that they employ are working or what they do. They don't publish technical specifications, and the closest you can really get is marketing and promotional material. So these don't really contain many technical details. It's usually high-level doublespeak. It doesn't make much sense. They usually use very pseudoscientific claims about things like threats and anomaly detection, this kind of thing, which isn't really very helpful. So it's really hard to evaluate the claims that they're making. So the purpose of this talk is really to help provide some of the missing technical specifications for Sophos. When you understand what it is they're actually doing, then you can make a more informed decision about whether this makes sense. I also wrote an accompanying paper for this talk. It's available to download. I think the URL's at the end. So the solution that antivirus vendors usually propose to help you evaluate whether their product makes sense is nifty castings. I'm not really sure that this makes a lot of sense. They tend to document their procedures, and they essentially have what they call a lab, and they have a big corpus of collected malware, and they just scan it and they run it and they say this is how they test whether the antivirus is a good quality or not. I don't know. It doesn't make much sense to me. It seems that this is no different really from reviewing a crypto system based on how random the output looks. I mean, it's not possible to do this. It's not possible to do the same. Yeah, they effectively just treat these things as black boxes, and they have little idea of what's going on behind the scenes. The security press tend to be non-technical, and they focus on usability and perception of security that these products have. At best, they have anecdotal ad hoc results by scans and emails or something like this. They simply don't have the technical expertise to effectively evaluate the claims that the vendors are making, and they have no option but taking up their word. So I've attempted to remedy this. So what I've done is basically reverse engineer the core Sophos antivirus engine, and I can explain how it works and what it does. So I don't have any proprietary knowledge about proprietary knowledge of access about Sophos antivirus. This is achieved entirely through reverse engineering and using tools and techniques that are easily available to any attacker. So this is any information that attackers wouldn't already have. So I'm not discussing any vulnerabilities at the moment, only design and implementation of Sophos itself. So Sophos is a widely used antivirus implementation. It tends to score well in industry tests. They ship a number of security-related products. The only one I'm discussing at the moment is the antivirus product, and this is the only one I've looked at. The latest version available is the one that I've looked at. I shared a copy of the paper before publication with Sophos, and they gave me some feedback, so I incorporated these slides. So I'm going to move on to discussing some of the components of Sophos. The first one is signature matching. So this is the marketing description that Sophos put on their website. I'll read it out. It says, Sophos dynamic code analysis technology utilizes sophisticated pattern matching techniques and identifies viruses by rapidly analyzing specific code sequences known to be present within a virus. Virus patterns are created to ensure that the engine catches not only the original virus, but derivatives within the same virus family. This isn't very helpful or really to understand what it is they're actually doing. The static file signatures are mainly the core mechanism that Sophos uses to practice non-malicious coding. So I reverse engineered their signature matching VM and the signature file format that they distribute to end users. and I've also written some tools that allow inspection of the signatures and to disassemble these signatures so you can read them. Yeah, I've also released source code so you can examine them yourself and create new signatures, in fact. So I'll talk a bit about the file format that they distribute. So the signature file format I distribute in a container format that they call subcontainers. The subcontainers contain subsections called petitions that can be extracted as appropriate, and each petition begins with an identifier describing the contents. The identifiers are things like petition list, table of contents, section list, and each section has a set of flags which can describe whether it's going to be compressed and encrypted before it's extracted. However, the only encryption algorithm supported is XOR, and the key is included in the file itself, so it's essentially just some obfuscation of the contents. And Sophos use an old version of Zlib for compression, and by giving you clip a flag in the section list that tells you the contents of the section list is compressed, and then they'll deflate it and then they'll inflate it at runtime. So all the files of Sophos just use the same container format and just different sections within the container. So this is a sample header from one of the container files, and you can see that they use this. They like this Microsoft style of using character constants, the multi-byte character constants, and you see TOC, table of contents, plist, partition list, section list, and so on. And yeah, it's a sample file. So the signature files themselves are signed. For authentication, however, they use a proprietary authentication scheme that they embedded themselves. So I prepared a more thorough examination of this, and I'll talk about it a bit later, but suffice to say that it's completely broken. The virus signatures are contained within these IDE sections of the files, and these contain variable bit chunks that describe the signature and have the signature matching the signature bytecode itself. So each signature definition contains the virus name followed by one or more bytecode programs to describe the file. The bytecode itself is executed on a proprietary VM for each input, and if the content matches, then it's considered malicious, and it's some further action taken. I've written some tools to extract and disassemble these, so you can read them, and it's possible to examine them in more detail. So this is a quick look at the virtual machine that they execute these bytecode programs on. So the VM itself is a simple stack-based machine with single byte opcodes, with variable width operands. There are some named areas and some registers that they use for basic calculations. So here are some examples. So I don't know what these opcodes are really called in Sophos source code. These are just from reverse engineering, so I've given them appropriate names based on what it looks like they do. So there are opcodes like CRC32, which will CRC32 the next n bytes of data, and they have a register that contains the offset into the current input file, and they can implement that to skip over bytes and so on. They can read words from the input onto the stack, and yeah, they can seek, do some basic calculations, and this is so they can move around the input and do their analysis. So here's a sample bytecode program that I've disassembled. This is for some random sample called attention 629. You can see that this is actually quite a complex example for a typical Sophos signature. They encode some literal bytes, then they CRC32 6 bytes, then they seek around a little bit, and then they do another CRC32, and that's it. So yeah, this one is actually above average complexity for a Sophos signature because it includes some file point communication, which is quite rare. Most signatures follow the same simple pattern, which is just identify a small literal pattern, usually 2 bytes, then CRC32 and the next sequence of n bytes, and then CRC32 the data following that for another n bytes. That's pretty much the format of a typical signature. So I suspect most of these are automatically generated because they rarely make sense. For example, they often check some irrelevant or dead code sequences, and often they're very small code sequences, just 5 or 6 bytes, and they don't seem to do anything particularly useful. So yeah, the core of the most signatures that I've examined is really been this CRC32, just some type sequence. Like, this is the core of the signature matching. I'm not really sure why they rely on such a weak scheme, because signature schemes with far superior properties have been published before this. It's well known. How to produce a scheme with far nicer properties. And yeah, so such heavy reliance on non-computer caching has introduced a number of problems with this scheme. So it's self-evident that one of the core goals of the signature scheme should be to minimize false positives. And in fact, this is a popular research topic. There's a large body of relevant work that Sophos is pretty much just ignored. In fact, it's so even though it's pretty easy to find collisions, basically just because they rely on CRC32 and it doesn't take that long just to generate without any knowledge at all. You can in fact automatically generate the images for many Sophos signatures, and I've written tools to do this that are available if you want to try this out. So for any given signature, you can pretty much most of the time you can automatically generate this an input will trigger it. So yeah, because generating CRC32 images is trivial. And even if it wasn't, the naive attack because it grew 32 bits per minute in quantity hardware, so it's not particularly interesting how to do it. And you can see I can generate this is a screenshot. I guess you probably can't read that. So you can verify that you can generate samples that match any Sophos signature. Sophos claimed that their researchers spend time creating good quality generic signatures. And I tested this claim by examining a random sample of signatures from their identity files. They have tens of thousands of these signatures, so I can't be exhaustive, but there's really very little evidence that they're aware of the context of the signatures they created, because quite often they CRC32 is completely nonsense code that is either very generic or a dead code or just something that's pretty much irrelevant to whatever the code is doing. There are some counterexamples. Like there are some code that checks, for example, just some important routine, but these are pretty much in the minority, and I'm not sure whether they just selected these by chance, because often they start perhaps not even at the beginning of a routine, perhaps in the middle of an instruction, something like that, which doesn't make much sense. So Sophos signatures are bytecode for distributed bytecode for this proprietary VM that they have, and they're pretty much wrappers around the CRC32. Even the non-automatically generated signatures tend to be poor quality, often matching irrelevant or dead code sequences. And I think it's fair to say that the signature scheme produces a pretty good best based on the properties that they themselves define as how they should be measured. So another major component of their product is the exploit mitigation service. And this is one of my areas of expertise, so I was interested to see what they were doing in this. So yeah, they sell a runtime exploit mitigation system that's only for Windows systems. I think it's a good idea that they're trying to do so, but their system is so badly broken and poorly researched that it's pretty much useless. It's not really necessary to defeat the exploit mitigation because they really didn't understand the problem they were trying to solve at all, and it really doesn't do very much at all. So defeating it isn't really necessary just because it doesn't really do, they didn't really understand the problem they were trying to solve. So the name of this product is called the Sophos buffer overload detection system. I guess it turned out very well. I'll read it out. It says a buffer overflow attack is reported when an attempt is made to exploit a running process using buffer overflow techniques. This detection system will catch attacks targeting security vulnerabilities in both operating system software and applications. And yeah, they say this is one of the core major components of the HIP system. So yeah, this is the BOPS, or Buffer Overflow Detection Service. It's handled by Sophos as one of the 4 layers of detection. But there's no technical documentation available to understand what it is it does. And in fact, the system was obfuscated. They distribute it in obfuscated form, so it's very hard to understand. but it wasn't much of a challenge to reverse engineer it once I understood the crypto they used. So it's actually implemented entirely in user space, and it's loaded in the address of processes using app-init DLLs. I say most processes because obviously app-init DLLs isn't universal. It's only applications using user 32. And basically what they've done is used Microsoft detours to intercept various APIs, and they insert their logic at these points. So yeah, you can see it loaded into any process that you use to my Process Explorer. If you have Sophos installed, then you'll see this DLL loaded. So although they claim that this works on all of the platforms that they support, but in fact that's not true. Although it loads on any version of Windows, it only supported on versions of Windows prior to Vista. And in fact, during initialization, if your version is Vista or higher, then it just doesn't do anything. It is loaded, but it remains loaded, but doesn't do anything until you go on. So they intended to implement two weak forms of runtime exploitation. So they have a simple SEH override protection, and they also try to do wet-to-libc detection and prevention. So let's just recap on the attacks that they're trying to mitigate. So SEH override was traditionally a very simple method of exploiting stack level of Windows. However, due to adoption of runtime integrity verification from Microsoft, this is pretty much new to the technique since Vista SP1, I think, Vista SP1 and higher. However, the two main mitigations are safe SEH, which has a number of drawbacks, basically because there are lots of cases where it can be easily defeated. But I guess as time goes on, this will improve. SEHOP is only available in Windows versions since Vista, so it's not entirely unreasonable to sell a product that implements this mitigation for XP. Although it turns out there are a number of good quality free applications, so it's not really necessary to sell one, but nevertheless, it does make sense. So SEHOP is essentially a solved problem, and this is mainly solved by Matt Miller from Microsoft. He's published most of the work on this subject. The solution really is to insert a canary at the tail of the exception handler chain, and then the system can check the integrity of the list at exception dispatch. And you can verify that the chain hasn't been tampered with and that it's safe to use it. And so Matt's implementation is public. As I understand it, it's different from the one that's actually shipped out of Windows, but it's the same basic concept. And Matt's implementation is called Wentrust, and it's available to download and examine. So this is the pseudocode for Matt's implementation, and you can see you basically just verify that the exception validation chain terminates at the correct location. And this is basically how SEHOP works in Microsoft Words. So Sophos implementation was clearly inspired by this because they basically got the same API and they tried to use some similar checks. But I think they misunderstood the entire problem. And for comparison, I read some pseudocode that you can to compare it with Matt's original implementation. So basically, they check whether the handler, the first two handlers point within the thread stack, and then that's it, and that's the entire verification. So yeah, so essentially they just verify the handler for the first two exception methods just don't point within the current thread stack, and that's the entire check. So that's pretty much ridiculously weak compared to the one that we published and publicly available. And even a low-skill attacker could just trivially defeat this. I think it's fair to say that Sophos misunderstood the published information on this topic, and that their implementation is basically a broken format of what is already a solved problem that they could have easily have reused. So the obvious attacker of this is simply to use wet-to-libc, but Sophos did consider this, and they implemented wet-to-libc detection. So just a quick summary of wet-to-libc. It was originally developed by Solar Designer to demonstrate weaknesses in early stack level mitigations. so some of these early attacks would focus on things like randomizing the stack or making the stack nice people. And it wasn't immediately obvious to early implementers that this was trivial to complete, and this is how they used it. It's still an important technique today, although the attack has been generalized over time, and now sometimes people refer to it as ROP. So a strong ASLR implementation is generally considered the best defense scheme to get to libc. But it's a fair observation that ASLR is not strong on all Windows platforms, particularly XP, where it's basically non-existent. So ASLR, if you can't predict where the code you want to return to is located, then you can't return to it. So this is why ASLR is a good solution for libc. So Sophos tried to solve this by implementing what they call protected functions. This is part of their BOPS system. So at load time, it basically passes an encrypted configuration file listing Windows APIs that Sophos believe are most likely to be used by attackers in their libc payload. So then these routines are hooked with detours, and then they insert their logic at this location. So from within the callback, they verified that the caller was from a recognized module and not within the current place, and that's the entire chat. So this just doesn't make sense. So Sophos really didn't understand the problem at all. They were confused because, I think they were confused because Solid Designer originally returned into an exported library function, which was system. You would just set the stack to it, so it could contain bin.sh, for example, and then return it to system. But Solid did this because it was convenient and because it was simple to do that. There was no technical requirement saying that you actually had to do this. And of course, this is how bot works these days. You don't need to return it to any specific code into any specific location. You can return anywhere the code that happens to make up anything that you want to do that's useful. So these days, these are sometimes referred to as cabins. And so finding collections of these useful code sequences is almost a science nowadays because of because it's such a common exploitation technique. So yeah, attackers can simply piece together what they want from other locations. But of course, if you just return the code immediately after the hook, then you don't even need to do that at all because it'll just work. So Sophos were attempting to enumerate their own bad, which just doesn't make sense in this context because you have the entire address space available to you. This just simply doesn't make sense. So Sophos returned libc mitigation is basically useless, and I don't think you should. I don't think anybody should use this or rely on it for security, simply because they misunderstood the problem and it doesn't prevent using any of the techniques that they were trying to prevent. So the configuration system for this itself is actually obfuscated. They keep the list of routines that they hook a secret, and there's also a list of image names in the configuration that they whitelist. It's encrypted with a hard-coded 64-bit symmetric key with using their proprietary encryption scheme called SyScan'11. But I've re-implemented this, and I've got my own implementation so that you can code it. And in fact, of course, they just hard-code the key because it's symmetric algorithm. However, for some reason, they also, after they decrypted it with this SPMA key, then they decrypted with XOR. They encrypted with XOR and hard-coded the 8-bit key, 0x93. I don't know what they were thinking, but yeah.
They were not thinking.
So yeah, I made a tool called SPMA util that you can use for encryption and decryption. Yeah, this is how you can decrypt the configuration file and see how it works. But it's not super exciting, it's just a list of Windows APIs that they think that you might want to return into when they check the caller. Of course, that's not going to prevent anything, but in case you want to see it. So yeah, they also have a list of image names that they apply their protection to. These are things like QuickTime Player, AppleRead32, and so on. So even though they say it protects operating system software and other software, it actually only applies to these ones that they've whitelisted. There's about 10 in there, and they're things you might expect, like Acrobat and so on. Anything else it doesn't apply to, even though it's still loaded into the address space, it basically just sits there doing nothing. So yeah, it doesn't apply to any other software except these. So I'll talk a bit about the encryption algorithm they use, which is they call SPMAA. There's no documentation for it. I know the name of it because there are some exported symbols related to this. And yeah, it's called SPMA32. So SPMA, it's a proprietary 64-bit bicycle block cipher that Sophos use in their products. In fact, they use it pretty much for any encryption that they use. They use this SPMA algorithm. It's undocumented and unpublished, and so obviously it hasn't been peer reviewed. And yeah, they use it exclusively for cryptography in their products. Of course, they also use XOR a lot for obfuscation. And so yeah, they've actually also used this for authentication of IDE files, and this is their signature scheme that they use. So it's obviously a very old encryption algorithm, and it's inherently weak because of the design. It's obviously 64-bit cipher. However, it doesn't look too badly designed. It probably was implemented by a real cryptographer. I'm not a cryptographer, but it didn't look obviously weak to me. And some cryptographers have looked at this since I released the code, and yeah, they've found easy key recovery attacks. But it simply doesn't matter because Sophos misused this throughout the products. It's used for authentication and secrecy incorrectly, and they've reduced it to basically an obfuscation scheme because they use it in cryptography modes that simply just don't exist. So yeah, so they repurpose this to sign their IDE files. So how they do this is there's a signature inside the IDE files that are downloaded from Sophos, and they basically truncate the 64-bit internal state of the file to 32 bits, and then they use that as the signature. So that's not a real cryptography. That's not a real cryptography. It just doesn't make sense. And in fact, even it's trivial to sign your own updates with this, just because it's obfuscation and not an encryption scheme. But even if you could do that, it wouldn't really matter because it's just 32-bit signature, and you can brute force it in minutes. So it doesn't really matter, even if it did make sense. What's interesting about this is that it makes transport security essential because Sophos simply, otherwise attackers can interfere with the product configuration and data files. But Sophos don't do that. Everything is downloaded over HTTP, and they rely on this signature scheme for security. And in fact, I think it would be hard for them to deploy something like HTTPS because they use Akamai for distribution, which obviously makes that quite hard. However, since I published my paper on this topic, Sophos have told me that they're going to migrate to a new signature scheme based on SSL. So hopefully they're going to solve it with a real signature scheme instead of trying to work around it. So yeah, I use tools to demonstrate this. They're available for download. So Sophos also use SPMA to encrypt sensitive product data. But yeah, it's a symmetric cipher, and every time they need to hide something, they simply just hide the key within the product, which doesn't make any sense. So yeah, and sometimes if they need extra security after the SPMA decrypted it, they XOR it as well. I don't know if they think that's the second layer or something, I'm not sure. It's trivial to recover these keys just using standard reverse engineering. And in fact, one of the useful keys I've extracted so that I can examine the configuration. So yeah, so Sophos using an obfuscation scheme where a real cryptography could have worked, and it's well understood and it's easily available, and I've got no idea why they didn't do that. There's no reason that they couldn't have a real signature authentication scheme on the updates, and obviously there's no way to really obfuscate any product data because it needs to be available at runtime for the product itself, but they can easily authenticate it to make sure it hasn't been tampered with, and they didn't do that. So regarding SPMA, they simply just don't use good quality encryption in their products, and they have and the encryption that they do use, it's misused, and they weakened what perhaps could have been a real, although pretty weak encryption scheme into an obfuscation scheme that's trivial to defeat. So yeah, and they try to augment this weak encryption with XOR on top of that, and this just doesn't make any sense at all. So Sophos rely pretty much on obfuscation for security because of this block system where they try to hide where they insert the hooks. But an attacker, even though an attacker wouldn't really want to understand it because it's trivial to defeat anyway because of the way it works, an attacker could, if it did work, an attacker could work out how it worked, work out where they were actually inserted. Although obviously you don't need to do that, so I'm not even sure. It's a bit hard to understand. So I talked to Sophos about this and the use of SPMA, and they conceded it was a weak scheme. And they told me that they're going to migrate to a real signature scheme in the next major version. And apparently they've already tested it on, they're already testing it for their Mac product. And I guess the next major version of the Windows product will have real signature scheme and real authentication suites. And so yeah, they're going to start phasing out the use of SPM8, which I guess is fast as hell. So yeah, they did understand the problem, and they were happy to say that they were working to improve that. So that's good news if you're a Sophos user. The next component I'm going to look at is called the pre-execution analysis. So Sophos attempts to work out what file they're looking at using using a magic system. If you're familiar with magic support on Linux, where you try to work out what a file is, and then you can mine that. Sophos has a role implementation that appears to be called WTF, which tries to work out what the file type that the file input that they're looking at is. So yeah, they use this to identify the container and archive file formats, and then they handle them quickly, which would be obviously trying to extract the content of an archive, for example. So yeah, for native executable code and dynamic HTML, they actually try to emulate the code inside the PDF, and they do this by embedding their own the JavaScript interpreter, and it's actually executed on code that's found in these files. So if it's native code, believe it or not, Sophos actually ship a simple x86 emulator that is used pre-execution on known executable types, and also unknown file types. They do this because it might be a .com file, which maybe, I mean, I suppose that's reasonable because there's no way to identify a .com file. Well, I mean, I guess it was probably reasonable 20 years ago. These days, I guess it doesn't make much sense, but they still do this anyway. So the emulator executes the code for approximately 500 cycles on a pretty simplistic machine. It doesn't have much hardware support. It doesn't understand anything like CPL or x87 or anything like that. The implementation is pretty inexact. For example, you can write to things like the test registers, for example, and that works completely fine. This is probably reasonable because it's probably it's designed for speed rather than accuracy, and the purpose is probably to allow basic unpacking support to run, for example, like XOR decryption and stuff like that. So they provide a very simple DOS and NT stub for operating system emulation. It's not a very good representation of x86. It's trivial to bypass or detect it, and if you were just to spin the 500 cycles, for example, that would just completely bypass it. Of course, there's no real solution to this problem, and no matter what number they pick, it wouldn't make any sense. It could always be defeated. It's just impossible. So many features of the emulator are simply broken and have never worked at all. The NT stub is a good example because they basically misunderstood the entire concept of how system calls work on NT. So it's hard to explain how it's possible to get this wrong, but they basically hard-coded the system call numbers for the emulator. And they actually hard-coded the system call numbers from the SSDT from a Windows Server 2003 SP1 kernel. And they didn't realize that couldn't work on any other operating system because, of course, Microsoft changes the system call numbers on every kernel. So, in fact, the system calls that they emulate will only work if the code is specifically written and they hard-coded system calls, using like int2e with the numbers from Windows 2003, Windows Server 2003, which of course just doesn't happen. So, it's and in fact, I looked at all the versions of this that were published to find out how long this bug has been in there. And it's basically always been in there, and it's still in there, and I guess they're afraid to change it because the system calls that they support are simply just not detected correctly, and they have no idea which ones have been used. So there are similar problems like this throughout the emulator. They didn't have much understanding of how this low-level stuff worked, so they tried to implement it, and I guess the guy who wrote it observed that it worked because he tried it on his Windows Server 2003 machine, and it obviously doesn't work anywhere else, and it never has. So the intention of the emulator is basically to record execution characteristics. Most of these are pretty broken because of similar bugs like this where they misunderstood how something worked. So some examples might be, for example, they try to record the first VMA that tries to execute the VTSE instruction, which they use as some kind of signature. So if VTSE occurs and, I don't know, offset 21 per page, that's a signature that they use. So yeah, and they also record memory references, and this allows simple decryption loops to work before they apply their static signatures from the bytecode VM I mentioned before. So it's not really of much use because even my adversary who spin a 500 cycle performance mapping, so it's not really of much value. And it's a really considerable chunk of attack surface, an x86 emulator. So this is also partially used for supporting other packers. But on top of that, they also have support for lots of common packers natively. So the native unpackers, yeah, unpackers themselves are used for software distribution. But the problem for antivirus vendors is that even someone who has zero skill at all can bypass these packers and basically transforming their input malware into a new piece of malware using packing. So you can bypass these C packaging schemes with zero skill just by running through the packet. So antivirus vendors, of course, realize this, and so they try to build their own support for common packers that a zero skill user can do. So of course it doesn't make sense because even if you're just a mod piece of a packet, you can just buy things with those up. But so for this reason, many vendors have support for large numbers of packers, and they visit this as a selling point. And they do include support for a number of pack formats. So these are some of the native packers it's called. These are some of the packers that are stored in native code. As you can see, this list is these are all pretty old packers, and some of them are from like 1989, 1992, and so on. And these are mostly DOS. Some are few, but mostly I think mostly the DOS, like things like LZX and KGLX is all very old. And with the exception of PE Compact, which it appears they licensed the code from packet from the vendor of PE Compact itself, the rest of them seem to be written by Sophos. I would say that these are pretty poor quality because they usually only support default options and codecs, and they're not tolerant of any modifications to be input by the tool. And in fact, I wanted to test this code because obviously this is a pretty big chunk of attack surface. But in fact, testing it was quite hard because they usually only support one very specific version. And I had to download dozens of versions from share archives to find the working inputs. And this took a long time. Things like, for example, the version of FSG, I had done like 20 versions until I found one that Sophos actually supported. So this is really a questionable value because obviously just download the latest version of Sophos won't handle it. So based on the amount of trouble I had to go through to find executables that were supported by Sophos, I think this massive increase in attack rate is really worth it. So even a naive attacker would just not have much trouble just by using the default version available. If you just typed in the name of it into Google and picked the first one, Sophos would detect that. And packers represent a pretty considerable attack surface inside Sophos because, of course, the confession algorithms are easily breakable and difficult to get right. And the packers that are actually supported this way are largely obsolete and irrelevant, and nobody would ever use them. I suspect this is mainly just to support industry testing that have this old corpus of viruses that they've built up, and they want to make sure that they can still report. It's not really much use, and it's such a huge attack surface, it's really a big mistake, I think. So they really do support a large number of container and archive file formats. But they vary in quality. Some are just completely bizarre or completely broken. Or have some kind of bizarre exceptions that just don't make any sense. For example, one thing I noticed, I was looking at that ELT decoder, and it specifically executes Siemens tricore executables. And this is just, these are used for industrial microcontrollers. ELF defines hundreds of different architecture types, and for some reason they specifically pick on Siemens Tribal. And there were similar weird exceptions in the other archive types. One of the major selling points of Sophos capable about it is their support for genes and genotypes. But this is pretty much undocumented, and it's basically most marketing. So they actually filed a patent for this, and so we can actually understand some of the rationale because you can read the paper that they filed. So the idea is pretty trivial. A gene, what they call a gene, is just any arbitrary characteristic that's either defined statically or in the core engine in identity updates. So yeah, any characteristic will do, such as any for example, a bytecode pattern or a matching regex with strings, or contains any particular contains some import that they're interested in, for example. Or it could be done at runtime using their x86 emulator, which might be, for example, divides by 0, or executes a reach SU instruction, or executes CQID, that kind of thing. And then they collect these characteristics together, and then they blacklist the combination of them. And this combination of characteristics is what they call a genotype. And then they blacklist the sequence of characteristics. So some of these characteristics are defined during p-execution, and some of them are defined statically. So one thing they do quite a lot of is pattern matching on strings within the executable. And these are actually used really heavily. I looked at some of the signatures, and the most common ones are things like embedded URLs or embedded IRC commands. That counts as a gene, and then in combination with import some W9 elite stuff, maybe that counts as, should be blacklisted. And so this is what they call genes in general. So I spoke to Sophos about this, and yeah, I sent them a draft of my paper, and they said that they're going to start making some changes based on my paper. So basically, what they said they're going to do first of all is phasing out the use of SPMOA, which is definitely a good idea because it's improvement. They're going to implement a real cryptographic scheme for signatures, which control is going to be based on SSL, which is good. And they're going to reevaluate the use of props because it basically just doesn't make any sense at the moment. So I think this is good news if you're a Sophos user. So yeah. So in conclusion, I think that Sophos demonstrates real naivety in lots of areas that is really key to the efficacy of any Android product. They misuse crypto. They rely on XOR everywhere. They misunderstand basic fundamental concepts that are really pretty important for an antivirus vendor should know about. Things like empty system calls. I mean, if you don't know this, I don't even know. And so yeah, even rudimentary exploitation techniques, things like ret2libc and SDH override. I mean, these are the basic security concepts, and they're trying to make a mitigation product, and they didn't even understand how it worked. I think this is pretty negligent in my opinion. So in my opinion, based on reverse engineering the product, I think that really Sophos technology is pretty ill-equipped to deliver on the promises they make about protecting end users. And so yeah, I think that's it.
Well done. Any questions? 有任何问题吗 ？Please do not be shy. 请不要害羞哦。有问题，任何问题都可以发。Any question? No one? No questions? Okay. But before you ask, let me ask my question first. Is there a reason why you choose Sophos and not like AVG?
No particular reason. I mean, like it's such a big task that you can only do one at a time. So yeah, Sophos just.
Right. So now you're done with Sophos. Are you going to move on to other antivirus?
No, I'm sick of antivirus.
Okay, fair enough.
Yeah. That was pretty much my question. I didn't really do any preliminary research to compare different vendors and chose Sophos because it was interesting, or was it just randomly out of a hat?
Yeah, pretty much just randomly, just had to pick one.
So, but this is your personal project. That's not part of what you do for Google.
No, it's personal project.
Personal project. All right. Okay. Any other questions? Anyone?
Do you suspect some are better than this, or do you think this is the state of
I would hope so, but I mean, yeah, I mean, I don't know. There were basic things about how they work, and if you want to know how they work, you really have to put some effort into this and do it. And they're not really good.
Was it your impression that they were surprised by your finding, or they knew they were okay? We got cash now. We got to.
Yeah, I think they knew that it was going to be very good, and especially I think the most embarrassed about the encryption was good. And yeah, so they said that they're always considering working on it.
Yeah, normally they will just keep it unwrapped until someone, say something about it. Yeah. But just let you know that the big antivirus company in Taiwan here is Micro. Yeah. So, anybody uses Sophos here? Any user? No. Any Micro user here? No. That's strange. Okay. Any questions? Please feel free to ask any question. Ben, you have a question?
No.
You don't.
I was just waving at someone.
Oh, you use Micro? Is that what?
No, just waving.
Okay. Last time, I'm going to ask this for last time. Any questions? Seriously, please feel free to ask any question. Tavis is still single.
What's the Wi-Fi password?
Yeah, backpacker. The Wi-Fi password is SyScan'2011. SyScan'2011. Okay, that's not a question. If you have no questions, all right. Thank you, Tavis, once again. We will have our coffee break now. Please feel free to go out, grab whatever food and drinks you have. That we have provided for you, and go to the NFI counter to sign up for the campus download. All right. 好，我们现在就休息，茶点已经准备好了。那到外面呢，请找新涌的他们新涌的人填。